Okay, let's start off with linear programming. So, what is a linear program? Well, it's one type of convex optimization, which is naturally of the form minimize f0 of x over x, which is an Rn, subject to fi's of x less than 0 and hi of x equal to 0. Here you've got I going from 1 till m and I going from 1 till p. So this is the general form of any convex optimization problem, and linear programming is one instance. The objective function f0 of x is affine or linear as follows. So C transpose x plus D, where D is in R, right? C and x are both in Rn, okay? And not just that, fi of x is also of the form gi transpose x plus hi, or let's put minus, but it's really the same. Hi of x's are of the form ai transpose x minus bi, right? So in other words, everything is linear. The cost function, the inequality constraints, and the equality constraints. Well, in convex optimization, the equality constraints should always be affine, right? But it happens that in linear programming, the inequality and the costs are also affine. Now, if you'd rewrite it that way, you'll have minimize. If you replace everything, so instead of f0, you'll write C transpose x plus D, subject to all your gi transpose x minus hi less than 0, right? And your ai transpose x minus bi are equal to 0, right? Well, this looks a bit, it's you could write it in a more compact way, because once you get your hi's over here and your bi's over here, then you have something like this. So instead of this problem, you could go ahead and express it in that way. So minimize over the same cost subject to gi transpose x less than hi, right? And ai transpose x less than bi. You can also go ahead and notice that if you stack all those inner products one on top of the other, so in other words, let's look here and stack all my i's, so all terms of the following form. So I say g1 transpose x is less than h1, g2 transpose x is less than h2, down till gm transpose, is it m? Yeah, less than hm. So if you look at, this vector right here, you could easily see it as a matrix times a vector x, gx. And this guy right here is a vector h. So in many references, you see that you have this vector is less than, in that sense. So the less than is or equal is expressed in that way, which means that it is not a semi-definite positive inequality, because those are vectors. It means entry-wise, okay? So this is entry-wise less than or equal. So, and in a similar way, you could express AI transpose X, sorry about that, it had to be equal, AI transpose X equal to BI as AX equal to B, where B are all your B entries, right? So until BP. A would be all your vectors of the form A1 transpose stacked on top of A2 transpose stacked on top of down till AP transpose, okay? So all this, we can go ahead and write it as such. You'd want to minimize over the same cost subject to the matrix GX less than or equal to H, and AX is equal to B. So this is a linear program in its most compact form, LP, okay? Now, if we take a look at, the feasible sets of the problem, right? Which is the set defined by the constraints. So if I go ahead and, plot it, visualize it. So let's say I'm in 2D, right? Say I have this and I come and tell you, okay, so you have inequality constraints of the form, I don't know, have this line, everything on the bottom of this line, right? Maybe this inequality is, I don't know, x plus, no, x is too much. It should be half x, depends how you discretize. So half x maybe plus, say this guy is 3. So half x plus 3 is my first inequality constraint less than, I don't know, something. Let's say I come and put this line right here and tell you I'm in this region right now. And I tell you all x's that are positive. So I also bound you here and here, okay? So in the end, your region defined by the inequality constraints is this guy right here, okay? So the inequality constraints tell you that you have to minimize the cost function only in this region, okay? And in case you have equality constraints, right? Well, let's say one equality constraint is, I don't know, the x's that belong on this line. And also, I don't know, let's pass a line, right? So two equality constraints, which are defined by those two lines. And I tell you, voila, you have to minimize your cost function right here. Well, if you take a look at the feasible set, well, I drew it in 2D, but in general, in n dimensions, it is nothing other than a polyhedron, because it's just an intersection of hyperplanes, and thus a polyhedron, right? So the feasible set defines a polyhedron. This, you have to keep it in mind. So in general, in n dimensions, your feasible set, including the domain of F0, which is the feasible set, is a polyhedron and looks therefore something like this as an example, right? No, that's not right. Something like this, okay? This is your feasible set. Now, in linear programming, you'd want to, minimize over this set. And therefore, once you define the level curves, which are, defined by the normal vector of which is C, the vector C. So let's say C is pointing that way, okay? So all your level curves, i.e., all curves defined by the equation C transpose X are of the following form. So they look something like this. And this is not C, this is minus C. So if your C is that way, your minus C is the opposite sense. Okay, so those are the level curves. Find my minus C. And by the way, in general, people omit the D because it has no effect on the problem. Whether you're minimizing, 2x plus 5 or you're minimizing 2x. So it's the same, right? The minimum value of the function is attained at the same point x, whether it's 2x plus 5, 2x, or 2x plus million, it's the same value because you're only lifting by a value d, right? So if your function looks like this, and let's say this is 2x, and you're minimizing over, let's say here, just for the sake of simplicity, your minimum value is here. Whether you lift it up or you lower it down, it's the same, right? Doesn't have any effect on the problem, i.e. it doesn't have any effect on the optimal x star, okay? So usually people omit this d right here. So if you see an LP in standard form, right, without the d, don't panic. It's equivalent. It's the same problem you're trying to solve with your d or without. Okay, now going back to the feasible set right here, and we're trying to minimize the function C transpose x plus d or C transpose x over the polyhedra P. Right here we have a P. So there is a very nice geometrical interpretation of the optimal solution, which is x star to the problem. Okay, it is in fact proven to be as far as possible towards the direction minus C. So if this is your feasible set, your x star is going to lie, if we come and draw a level curve right here, right? So all those are defined by C. So your optimal solution is going to lie somewhere here, okay? This is your x star. This is actually a fact. Okay, so this is one geometrical interpretation of an LP, and there's other forms that are widely spread, that are ubiquitous, that are, you find them extensively in the literature. Actually, we have two famous LP forms that are the following forms. So the first one is, people do not like to see, gx is less than h, the inequality constraints as such. They prefer to keep it simple. So they tell you, okay, minimize your objective function, C transpose x, subject to your equality constraints, ax is equal to b. However, your x's are all positive. So it's the same problem, huh? It's not that we, the gx less than h is omitted and therefore we're not solving the same problem. No, there's some tricks that could be done to transform a problem of this form to this form, okay? So just to give you an example, gx is less than h could be transformed to the following. So I'll give you the thing in 1D and we'll extend it to ND. So let's say you have a 2x less than 3 is one inequality and the only inequality constraint. So what people do is that they add something called a slack variable, 2x plus s, and s is for slack, and they say, hey, 2x plus s is equal to 3. So you lift 2x by a positive amount of s such that it hits 3. And you tell me s is positive, okay? So what have we done by rewriting or manipulating this into this? One thing, we've introduced one variable to the problem, which is s, right? And two, we've omitted this inequality constraint and we've transformed it to an equality constraint, right? And one more thing is that you've, as a consequence, you have one slack variable which is positive, which is of this form. So this, where does it go? It is absorbed by the equality constraints, right? And that's it. That's basically it. You've added one variable, the slack variable, and you've told me it's positive. What have we done? We've increased the number of variables to minimize over, which will increase also the complexity of the problem, of course. But you've omitted somehow your inequality constraints of the form gx less than h. So this guy right here is called standard form LP. So once you do this, it's a standard form LP, okay? And you've got another type of LP, which is the inequality form LP. So if you do not have any equality constraints, in other words, if you minimizing C transpose x subject to ax less than b. If you encounter this problem, well, this is known as an inequality form LP. So let's do this more formally. Let's see it, because when we introduced the slack variable here, it was for one dimension, and there's one more thing. So your x is still a variable, right? But there's no guarantee that it's positive. So how do we go over that? So let's go back here to the standard form and, address the problem more clearly. So an LP is of the following form. Again, minimize C transpose x subject to gx is less than h and ax is equal to b. Your task is to write this as you write another problem which solves the same, the same problem, which is this one, the LP, but without the inequality constraints. I don't want to see any inequality constraints other than this. So transform an LP to a standard form LP. Okay, so the first thing that we did was, we introduced a slack variable. So this we can come and write it as such, minimize C transpose x subject 2 gx plus s, which is a vector, is equal to h, right? And ax is equal to b, where all my s's are component-wise positive, right? Okay, this solves half the problem. Why half? Because your x's, which are also still part of the problem, so we're minimizing with respect to x and s, okay? Don't forget that. Here, we were minimizing only with respect to x. We introduce now auxiliary variables, which are the slack, that are the s's. Okay, so your s's are positive, but there's no guarantee that all your variables, which are the s's and x's, are positive. So what do we do? A very smart trick that people do here is they decompose x into a difference of two positive numbers, x plus and x minus. Okay, so you just write down your x as a difference of two positive numbers. It is doable, right? Let's see. Let's see an example right here. So in 2D, 1 and 2, how could we write that? There's infinite ways of writing that, right? So 1 could be written as 2 minus 1, so positive and positive. And 2 could be written as 3 minus 2. Is this positive component-wise? Yes. And this? Yes. Now let's say I have a minus 2. Well, you can choose a 3 and a 5. Is this component-wise positive? Yes. Is this? Yes. So what I mean to say is that any vector, whether it has positive and negative entries, x, could be decomposed into a difference of two vectors which are in turn component-wise positive. Voila. So this is component-wise positive, and so is this. So what does this do to our problem? So if you replace x as such, you get this. So now you're minimizing this time over x plus, x minus, and s, right? Let me fix my x plus. C transpose x plus minus x minus, right? Subject to g x plus minus x minus plus s is equal to h, and a x plus minus x minus is equal to b. And now you've got s positive, x plus is positive, and x minus is positive. So congrats, all your variables are positive. And there's one more thing to verify. Is this linear in my variables? It looks linear, but let's write it in this form. So now let's call my variable z, okay, which contains x plus, x minus, and s. Can I write this as linear in z? Let's see. So this is equivalent to minimizing with respect to z, so right here, C transpose x plus minus C transpose x minus is C transpose x plus minus C transpose x minus, right? Can we write it as a, C transpose z or C bar transpose z? Well, yes, we could. How? Let's see. So if I come and multiply z with, C and a minus C and a 0 vector, right, of compatible sizes, transpose z, and I call this my new C or my extended C, CE, right? CE transpose. So my CE would be, C minus C and a vector of all zeros. Okay, looks good. Subject to. So this solves my objective function. My objective function is no doubt linear in z. So subject to, my constraints. So the first constraint I have is g x plus minus g x minus plus s is equal to h. So which could be written as such. So g x plus, as we did right here, minus g x minus plus s is equal to h. So as ax plus minus ax minus is equal to b, right? With z being this time all entry-wise positive, right? Now let's try to write those two equality constraints as one equality constraint of the form e, so an extended a, times z is equal to b e, an extended vector b. Could we do that? Well, yes, we can. How do we do that? So if my z, which is x plus, x minus, and s, how do I choose my AE and BE so that they reflect the two equality constraints? So the first one could be, x plus is multiplied by g, x minus is multiplied by minus g, and s is multiplied by I, the identity matrix. So if I do this block multiplication, I'm going to get the first equality constraint, which is my h, right? And the second one is x plus is multiplied by a, x minus is multiplied by minus a, and s, there's no s, so we multiplied by a 0 matrix, is equal to B. There you go. So this is my AE, this is my Z, and this is my BE. Okay? So we've transformed all this, right? All this to something that looks like this. Minimize C, E, transpose Z, subject to AE. Z is equal to B, where my Z's are positive. If I zoom out a bit, scroll up, I zoom out more. Is this problem the same as this? Yes. My C, my X, the Z right here is playing the role of X, right? My C is playing the role of CE. The A's and B's are playing the role of AE and BE, right? So, all in all, we can say that we transformed the LP to a standard form LP thanks to the slack variables and the decomposition of X into a difference of two entry-wise positive vectors. So I'm just going to grab some examples out of Boyd and Vandenberg's book entitled Convex Optimization, and I'll just discuss them right here. So yeah, the first really nice example that gives you an intuition of what's going on in linear programs is the diet problem. So let's say you're on a diet, and at the same time, the diet, you should have a proper schedule, proper list of nutrition or food that you would like to eat. And at the same time, this diet costs you money, right? Because to ensure a proper diet, you should have also a proper budget. So you have this push-pull or black-white dilemma that is going on. So this problem could be indeed formulated as a linear program. So in other words, let's denote your x vector, which is composed of n entries, and let each entry, so xk, the kth entry of x, denotes the quantity of the kth food, right? And at the same time, your vector c, c1 down to cn will denote the cost of the kth food. If we go ahead and look at c transpose x, which is nothing other than the sum of ck, xk, it is the total cost of your diet, right? So the sum of this product is the total cost. If you look at the objective function and you interpret minimize c transpose x over x, where x is indeed entry-wise positive, right? Because you can't have negative quantities of food. So if you look at this by itself, you're just trying to minimize the quantity of food. But if you solve it as is, the solution is clearly x equal to 0. So you will starve. So in other words, you will not pay anything, right? But you will starve. That is not a good solution. And this is where the constraints come in. We do not want to starve. How do we reflect it? Using constraints. We put a bound on the food we would like to take, right? We say that, okay, let's say the healthy diet would require me to take at least a nutrient. Let's take a look at a vector b, which will reflect the nutrients. So b1 down till bm variables, the bk would denote the nutrition of the kth food. The b vector reflects the minimum amount of nutrition I want. So it will serve as a lower bound, less than b, something like that. But since we're taking a look at, so my x's reflect quantities of food, I cannot directly compare them with b. No, there should be a weighting ax, or a matrix multiplication that transitions me from quantity x to nutritions b. In other words, the matrix A contains elements aij, where aij is the amount of nutrition I in 1 unit of food j. So nutrition in nutrient I found in 1 unit of food j. Okay? So we have an affine objective function entry-wise x positive, and ax is greater than b. But if we take a look at this, if we want to, compare it to the standard form of a linear program, which is minimize c transpose x subject to gx is less than h, ax is equal to b, you could just like flip this inequality by multiplying by a minus, and you'll get minus ax is less than minus b. So this is similar to this. And x positive, you can multiply by, I don't know, minus as well. You get x less than 0. And those two could be stacked on top of each other like this. So minus a right here, your x is here, less than minus b and the 0. And here you've got a minus I, right? So this is equivalent to this. This is your g, and this is your h, and no equality constraints. So all in all, the diet problem is a linear program. Okay, so this is not the diet problem you find as is. Of course, there's other variations on this problem. Okay, so now let's talk about some solvers that could solve your linear program in an efficient way. In this lecture, I'll be talking about a really important solver that is called the simplex method, which was discovered by Dantzig. And this method, the name of this method, simplex, is not to be mistaken with the polyhedra simplex, which is, so simplexes are another family of polyhedra. Now, polyhedra, we talked about it here in convex sets. They are, the intersection of hyperplanes and half spaces. Now, the simplex method is really efficient. We'll see just a bit from now how efficient it is, because we're going to be discussing it. We're going to be implementing it in MATLAB, and we're going to be using also MATLAB's toolbox as well to implement it and see the difference between our implementation and MATLAB's implementation. Okay, so now the best way to go here is to give an example and work it step by step. Okay, let's say you're given the following optimization problem. So you're interested in maximizing, okay, a certain cost, which is, I don't know, maybe 1,000 x1 plus 1,200 x2, right? Subject to some constraints, which are, let's say, 10x1 plus 5x2 less than 200, 2x1 plus 3x2 less than 60, x1 less than, I don't know, maybe 34, and x2 less than 14, given that x1 and x2 are positive quantities. Now the question is this a linear program? Well, it looks linear, but let's put it in its standard form. So standard form, as we talked down here, standard form LP, it is to minimize a certain cost subject to equality constraints. Now, minimize, maximize, I'm not going to comment on that because, all you see here is equality constraints. So the first task before implementing simplex or running simplex, you have to transform all your inequality constraints to equality constraints. So here we've got 4 inequality constraints. As we discussed just right now, the way to transform those constraints is by adding a slack variable. Okay, so what I mean is to introduce 1, 2, 3, 4 positive variables to lift the left-hand sides to be equal to the right-hand sides. So let's say those variables are, so I'm going to write here, so we're still maximizing the same cost. However, my constraints will now look something like this. So the left-hand side is the same, the right-hand side is the same, so as this, and this, and this, right? So we're just going to, lift. So we'll add a positive quantity. So let's say here we add x3, here we add x4, right here we add an x5, and here we're going to add an x6. And we lift it such that the left-hand sides are equal to the right-hand sides. Of course, this could only be done when the variables that I introduced, called slack or latent as well, or hidden variables, are positive. x5, x6, they're all positive. Now this is a program in standard form. So now we're ready to run Simplex. So this is it in standard form. Let's see how Simplex works. So first of all, I'm going to denote my objective function as z. So all this is denoted by z. And my objective is to maximize z. Now the first thing here to notice is how many variables do I have? I've got 6 variables right here, x1 down to x6. So my n, which is the number of variables, is equal to 6. And how many constraints do I have? I have m is equal to 4 constraints, right? So 6 variables and 4 constraints. How many solutions do I have? You have an infinite number of solutions. But we want to choose the one that lies in the feasible set. Okay, the one that lies in the feasible set. Now you have to keep something in mind. We really don't care about x3 down to x6. So it's okay if, you know, 1 or 2 of them are, you know, they don't reflect any quantitative explanation, right? So what people do here is, you know, they first set any certain amount of variables to 0 and launch the simplex method, okay? So those variables that you first set to 0, so you set n minus m variables, which are 2 to 0, they're called the non-basic variables. So without loss of generality, let's pick x1 and x2 to be 0. Indeed, you can pick any other 2 to be 0, right? But for just the sake of argument, we're going to pick x1 and x2 to be 0. And those are called non-basic variables, okay? And the other variables are my slack, right? x3, x4, x5, x6. There's slack. Now one might ask the following question. What if I had an inequality in the other sense? What if this one was x1 greater than 34? Can I still add a slack variable? Well, that's a really good question, and the answer is no. You cannot add a positive quantity. Instead, you would subtract a positive quantity to attain the right-hand side. So x1 minus, let's say s1 is equal to 34 would be your, you know, equivalent constraint, given that s1 is positive. In this case, we do not call s1 as a slack. Instead, it's called a surplus variable or an artificial variable. In French systems, it's called valeur artificielle, something like that. Now, we have set 2 variables to 0. They're called the non-basic, and the rest are slacks. And they're usually initialized to be the right-hand side. So x3 is usually initialized by simplex to be 200, x4 to be 60, x5 to be 34, and x6 to be 14. Well, that's natural because x1 and x2 are set to be 0. Therefore, you're only left with your slacks. And by construction, they will be equal to the right-hand sides. Okay, so now I'm going to start iterating the simplex method. So we'll start iteration by iteration. Okay, right here, I'll make me some space. And we'll start with iteration number 0. What does iteration number 0 mean? It means when you're initializing your problem, this is the first iteration, how it looks like without any operations. So there's going to be a vector of coefficients called Cj, or simply C, but in a lot of references, such as in operational research or stuff like that, they usually call it the CJ. So CJ is going to be a 1 by 6 vector indicating the coefficients of each variable, x1 down to x6. Now notice that x1 is multiplied by 1000, x2 is multiplied by 1200. So the CJ for x1 or C1 is 1000, C2 is 1200. C3 down to C6 are all zeros because they do not appear in the cost function. Therefore, they have no contribution to the cost. And hence, my CJ will look like this. 0, 0, 0, and 0. Now, there is something called the simplex table, and it consists of the variables that are, operating to reach the optimal solution. So since we have set x1 and x2 to be 0, they do not, or they are not in the simplex table. The ones in the simplex table are the basic or the slack variables. So we're going to stack them here, x3, x4, x5, and x6. Okay, and each row over here is a result of a constraint. So the first constraint should appear here, the second one here, third and fourth. And each column from here to here is, or will reflect my variables, x1, x2, x3, x4, x5, and x6. Okay? Now, the first constraint had a 10 multiplied by x1, so I'll put a 10 here. Had a 5 multiplied by x2, so I'll put a 5 here. 1 by x3, and the rest do not appear. Next, we had a 2 by x1, 3 by x2, nothing here. 1 by x4, 0, 0. 1 right here, nothing here, nothing here, nothing here. 1, 0. Nothing here, 1 here, 0, 0, 0, and 1. Now, usually also in some references, you have an additional column right here reflecting your CJ. So the CJ for each of those variables, x3 down to x6, are zeros, right? So 0, 0, 0, 0. So this is a column for CJ. And this is a column for your active x's, or your basic variables. And this is a column for their current values. Okay. Next, you have another quantity in your simplex, which is called zj. And you simply obtain it as such. So for each x, you have z. So z1 down to z6. I'm going to shift those because they look ugly. I'm going to shift them like this. So 1000 again, 1200, 0, 0, 0, and 0. And okay, so again, Zj could be obtained using this matrix right here and the C. And it's nothing other than each vector multiplied by the C vector right here, the size 4C. Okay, so it's 10 times 0 plus 2 times 0 plus 1 times 0 plus 0 times 0, which is 0. 5 times 0 plus 3 times 0 plus, it's also 0. You can go ahead and verify as the same till x6. Okay? We're also going to keep track of Cj minus Zj, right? It is going to serve as a stopping criteria. So Cj minus Zj right here is 1000, 1000 minus 0, 1200 minus 0, and the rest are zeros. And of course, the last but not least, we're going to keep track of our cost, Z. So Z is the objective function, the value of the objective function we're going to keep track. And currently it is 0. A good way of computing this, once you're implementing it using any software or any programming language, is using those coefficients right here. So if those, I call them my b's, right? It would be c times b. So 0 times 200 plus 0 times 60 plus 0 times 34 plus 0 times 14. It's a 0. And at each iteration, it should increase because we're maximizing, okay? Now, this is iteration 0. This is how you should set up your problem before starting any operation. Now, this is going to take us to iteration 1, of course, iteration 1, where we should be able to answer the following questions, or at least extract the following information. So we need a pivot. At each iteration, we're going to extract a certain pivot value. It's going to be one of those values right here, okay? And this pivot is going to serve as a value to modify all other values, okay? There's going to be a variable that enters and a variable that's going to leave. So what I mean by this is that we're going to grab a row thanks to the pivot, we're going to remove it, and we're going to enter another value or a variable, or insert another variable. So right now we have the following variables that are outside. So x2 is outside and x1 is outside. And in case I want a variable to enter, it's going to be x2 because x2 has a higher cost, has a higher coefficient, 1,200, and x1 has 1,000. Okay? And the variables that are in are clearly 3 times 6. Okay? Okay, good. Now, how do I choose my pivot? That's the first question. Because based on the pivot, I'm going to enter and leave a variable. Now the pivot okay, so the pivot is picked according to the largest value in the vector c minus z. So in our case, it is 1,200. So the pivot should lie in the column corresponding to 1,200, or the column corresponding to the variable x2. So which one is it? Is it 5, 3, 0, or 1? Well, the simplex criterion tells you that it is based on the smallest ratio between b and those values. So here we have 200 over 5, which is 40. We've got 60 over 3, which is 20. We've got 34 over 0, which is infinity. And we've got 14 over 1. Now, of course, in practical implementations, you're not going to divide 34 over 0. When it's a 0, of course, you're not going to choose it because it gives you the largest value. And there's no need of computing it. And last but not least, 14 over 1, which is 14. So the smallest of all those values is 14. And therefore, the pivot is 1, right? This means that the variable x6 has to leave and variable x2 has to enter because it's the one waiting in the non-basic variables. It's the one with largest priority, if you will. Okay, so now what do we do before removing this, variable? We have to do as Gaussian elimination. So we have to eliminate 3 and 5. And this is done by row operations. So if this row is denoted by R4, this one is denoted by R3, R2, and R1, we have the following row operations. So instead of R2, I'm going to put How do we null out 3? By using R4. All we have to do is R2 minus 3R4, right? Similarly, how do we null out R1? We have to insert R1 minus 5R4, right? So let's do it here. So we still have x1, x2, x3, x4, x5, and x6. So if instead of R1, I put R1 minus 5R4, I'm going to get 130, 10, 0, 1, 0, 0, minus 5, right? Why is that? So 200 minus 5 times 14 is 200 minus 70, which is 130, right? 10 minus 5 times 0 is 10. 5 minus 5 times 1 is 0. 1 minus 5 times 0 is 1, 0, 0, and 0 minus 5 times 1 is minus 5, right? Now let's do this quickly for R2. We'll get 18, 2, 0, 0, 1, 0, minus 3. R3 is not affected, so I'll just copy as it is. And R4 is not affected, so I'll just copy it. Now, as we mentioned, x6 has to leave and x2 will enter instead with its cost, which is 1,200, and the rest remains intact. So 0, 0, 0, and x3, x4, and x5. Now, what happens to the three quantities z, c minus z, and z? Well, as we said previously, zj's are computed by multiplying those vectors by the extreme left vector, which is the c's, right? So 10 times 0, 0, 2 times 0, 0, 1 times 0 is 0, 0 times 1,200 is 0, add them up, you get 0, right? 0 times 0 is 0, 0, 0, 1,200. You do this for x3, you get 0, 0, 0. And you do this for x6, you will get 1,200. I'll just copy my cj up here, which will never change, right? So my cj will stay 1,000, 1,200. And now let's subtract cj by and zj. We get here 1,000. Here we get a 0. Here a 0, 0, 0, and minus 1,200. Okay. Last but not least, my z is now 0 times 130, that's 0, plus 0 times 18, that's 0, plus 0 times 34, that's 0, plus 1,200 by 14, that is 1,600, 16,800, right? So this is my current cost with those variables. Do we stop? Well, you only stop when all your cj minus zj's are non-positive. They're all 0 or less. We still have 1,000, so we do not stop, we continue. So we go down here and write iteration 2. Again, we have to choose our pivots, which decides who will enter and who will leave. My cj's will remain. And we forgot something, which is the q, if you will, the variables that are outside, right? So x1 has a cost of 1,000 because it was here, this q. So x2 entered. So we have x1, and the one that left was x6. And x6 has a cost of how much? X6 had a cost of 0. Now, based on this table, who is my pivot? Well, we said that we look at the largest cj minus zj, which is 1,000. So my pivot is going to be somewhere here. And which one do I choose? I choose the one with minimum ratio. So 130 divided by 10 is 13. 18 by 2, that's 9. 34 by 1, that's 34. 14 by 0, that's infinity. So I choose 2. And 2 is my pivot. which means that x4 has to leave and x1 has to come in. Now, as we did before, we have to null 10 and 1. How do we do that? Using row operations. So this is my R1, this is my R2, R3, and R4. All I have to do is, instead of R3, I put R3 minus 2, R2, and instead of R1, I put R1 minus, I have 2, I need to get 10, so minus 5 R2, right? Okay, so let's do that here. So instead of R1, I'm going to put R1 minus 5 R2, so this guy becomes 0, right? This one remains 0, this guy remains 1, x4, so 0 minus 5 times 1 is minus 5, 0, and minus 5 plus minus 5 times minus 3, that's minus 5 plus 15, which is 10. And we forgot the 130, so 130 minus 5 times 18, that is 40. R2 remains unchanged, so it's 18, 2, 0, 0, 1, 0 minus 3. R3 minus 2 R2, that is, sorry, this is a half, so half R2, because half times 2 is 1, and therefore they will null out. So R3 minus half R2, which is R3 minus 0.5 R2. So R3 minus half R2, 34 minus half 18 is 34 minus 9, that's 25. Here we get 0, 0, 0 minus half, 1, and 3 over 2. And x2 is unchanged, so 14, 0, 1, 0, 0, 0, 1, right? And one last thing before inserting x1, the pivot that you pick should always be normalized to 1. So this row, we're going to divide it by, we didn't do that in iteration 1 because it was already 1. So here it's 2, so I'm going to divide R2 by 2. And hence 18 becomes 9, right? 2 becomes 1, 0 stays 0, here as well. 1 becomes half, 0, and here we have a minus 3 over 2, right? Okay, now let's insert x1 here instead of x4, and the rest remains unchanged. So x3, x5, x2, and x1 comes with its cost, which is 1,000, and the rest remains unchanged. Now let's compute the three vectors, or three quantities, which are zj, cj minus zj, and z. So zj is nothing other than those vectors times those vectors times the costs, cj. So 0 times 0 is plus 1 times 1,000 plus 0 times 0 plus 0 times 1,200, that's 1,000. 0 times 0 plus 0 times 1,000 plus 0 times 0 plus 1 times 1,200, that's 1,200. Same thing here, we get 0. Right here we get 500 due to the half by 1,000. This is 0. And right here we get 0. Right here we get minus 300, right? Now let's compute c minus z. Here we get 0. Here we get 0, 0, minus 500. Are we all negative? Well, no. If this one was minus 300, we would have stopped, but it's not. It's positive. We need them all to be negative. Now what is my cost? Z, it is C by B's. So 0 times 40 plus 1,000 times 9, that's 9,000, plus 0 times 25, we're still 9,000, plus 1,200 by 14, that is 25,800. As you can see, my cost increased. It was 16,800, now it's 25,800. That's no surprise because x2 is still there, but we have x1 with its cost, which is 1,000, right? So x1 came with its cost, and therefore it will contribute with 1,000 by 9, which is 9,000. You can see 9,000 plus the previous cost is the new cost, right? Okay, good. Now, since all my Cj minus Zj's are not negative, we have to go to iteration 3. Again, we have a variable that enters, a variable that leaves, and the pivot. And we forgot to update our Q right here. So this is the Q. So x6 is the next one to be entered because x1 already entered. And the one that left from iteration 2 is x4, so we'll stack it here. x6 has a cost 0, right? And x4 as well. Right, so now let's copy my Cj. Okay, now let us pick our pivot. And it's, as we said, based on the largest value of Cj minus Zj, which is 300. So the pivot should lie somewhere here. And it's based on the minimum ratio between this column and the B. So 10 over 40 is a quarter. Minus 3 over 2 by 9, that is based on the smallest ratio. So 40 by 10, that's 4. 9 by minus 3 over 2, that's 9 times 2, which is 18 over 3. That's 6, or minus 6. 25 by 3 over 2, that's 50 over 3, which is something like 16.6. And 14 by 1, that's 14. Now we choose the minimum in absolute value. We have 4 minus 6, 16.6, and 14. So it is 10. So 10 is my pivot, right? 10 is my pivot. That means that x3 has to leave and x6 has to enter, right? But before leaving, we have to do the row operations. So instead of R1, we're going to put an R1 by 10 to normalize. Instead of R2, we're going to put an R2, we're going to add 10 over 3 over 2, which is 1.5 R1. Instead of R3, we're going to put R3 minus 10 over 1.5 R1. And instead of R4, we're going to put R4 minus 10 R1. I'm doing the math really quickly. So the first row is divided by 10. So it would be, the second row would be 15, 1, 0, 0.15. Minus the third row would be 19, 0, 0, minus 0.15, 0.25, 1, 0, and the last one would be 10, 0, 1, minus 0.1, 0.5, 0. Remember that x3 left and x6 enters. So right here we have x6 and the rest remains unchanged. So x1, x5, x2, and the costs are still as such, right? Now let's compute our Zj, Cj minus Zj, and Z. So Zj is going to be this column by this one, inner product, or pointwise multiplied, then summed up, or this vector transposed with this vector. So we'll have 1,000, 1,200, 30, 350, 0, 0. Now C minus Z, that's 0, 0, minus 30, minus 350, and 0, 0. And this will be our And this will be our last iteration because all those entries are negative or non-positive. And last but not least, our final cost would be those quantities by those quantities, meaning that C's with the B's. 0 times 4, that's 0, plus 1,000 times 15, that's 15,000, plus 0 times 19, that's still 15,000, plus 1,200 times 10, that is 27,000. This is our final cost. And it is attained at the optimal values, x1 star and x2 star are equal to, so this is x1 right here, this is x1 equal to 15, I'm going to highlight it, and this is x2 equal to 10. So those are our optimal values, of course given by Simplex. Okay, good. So that's how Simplex works. Next, we're going to try to implement it on MATLAB. And we're going to do something really cool. We're going to, let's say you want your code to work for a very lazy person. Let's put it that way. So you don't want, the person to, as we did right here, namely, we don't want to convert it to standard form and, we add the slack variables, right? And we don't want, us to, think if this is a variable that is a surplus or artificial or I don't know what, slack. We want the program to do all the work for us, right? So how do we do that? So I've got MATLAB open right here, and I created a file called simplex.m, and I'm ready to start coding. So the first thing I want to do is clear my workspace, right? And the first thing that I'm interested in is to read, the cost function. I would also want to know if my cost wants to be maximized or minimized. And last but not least, for the first instance, I would like to know the number of constraints, right? So I'm going to do it in a graphical user interface style. So I'm going to imagine that a window is going to pop up and it's going to ask me all those 3 pieces of information. So the first thing, I'm going to give a title for my window and call it enter your LP data, right? I'm going to ask 3 things, which are going to be in a 3x1 cell. Those are the 3 things. What am I going to ask? I will ask the user to enter his cost function in the form of a vector, so the C vector. So in case you don't recall, when we started explaining linear programming right here, the way it was formed was C transpose X. So C transpose in this problem would be a 2x1 vector containing 1,000 and 1,200, right? And X would be x1, x2. So when you inner product or do the C transpose X operation, you will get your cost function. Okay, so we're going to get it as a vector, and we're going to ask the user, do you want to maximize your cost? If yes, enter 1. Or do you want to minimize your cost? If yes, if minimize, enter 0, enter 2. And last but not least, what is your number of constraints? This is what we're going to be asking from the user. Now, in the fields, let's see how it looks like right now. So if I open an input dialog with the prompt, so this is what MATLAB does. It helps you with the autofill completion, with the auto suggestion. So it tells you what to fill right here. So your prompt, your title, number of lines, I'm going to take 1 line, and default text. Let's not input anything for the moment. Let me run this. So I've got the following. Now that looks good. That looks really good. Let's see what happens when I enter like rubbish. So here I'm going to enter this 1 and 3. Okay. As you can see here in my workspace, I've got A being a 3x1 cell containing the values I just inputted. So A will contain this. Now what happens if I really enter a vector? Let me run it again. So 1, 2, 1, 3. So this time C is a vector. Okay. Show me my A. As you can see, A, the first entry is a vector, but it's in a char type. Those 2 apostrophes you see here means char. So we need to, cast it to an array, right? Well, I still don't like how it looks like because because I want the user to know that those two brackets mean a vector. So the way I can do this is using the default text. So I'm going to, for each field, give a default text. So for the cost function, I'm going to give brackets as such. And for everything else, I'll leave the user to understand that it's an integer. You have to enter an integer, or in this case, a boolean, 1 or 2, right? And I'll just pass it right here. So default text. Run. As you can see, by default, we get the brackets. Okay? Okay, good. Now let's cast it towards something we need to work with. Now, the way you can access your cells, say you entered 1, 2, 1 right here, and a 4 right here. The way you access cells, not array, this is not an array, this is a cell, is by using curly brackets. So A1 would return 1, 2, right? A2 would return 1, and A3 would return 4. But those are chars, again. So we need to cast them, means you're executing MATLAB expression in text strings. So let's say for the moment, we have a text string which contains 1 plus 2, right? As a text, it is 1 space plus space 2, or white space 2, right? And what happens when you say eval 1 plus 2? It will return an integer 3, evaluating the text expressions. Evaluating my A1 would be a vector. So eval A1 is a vector. Now, what type of minimization? Is it a minimization or a maximization? Depends on A2. Is it a 1 or is it a 2? And the number of constraints is a 3. Okay? Okay, good. Now, this is my first window that I need to ask the user. I'm going to based on the number of constraints, I'm going to open windows per constraint. Okay? So what I mean is this. Let's say I entered 1, 2 right here, and a 1 here, and 3 here. Because I entered 3 constraints, I want to know, because we're lazy, I want to know if each constraint, it has a less than sign, a greater than sign, or simply is an equality, right? So the way I can do this is based on the number of constraints. So I'm going to open a loop right here for n is equal to 1 to number of constraints. Let me keep it I till number of constraints. I'm going to open as many windows as the number of constraints. And each window has the same title, so because we're dealing with our constraints. Inequality or equality, so insert brackets. Inequality constraints data. Okay. Now for each window, there's going to be a slightly different prompt, a slightly different text saying, specify whether you want a less than, a greater than, or simply equal for constraint number 1, 2, and so on, right? So how do I do that? All I have to do is cast number to string. And what is the number keeping track of the constraint number? It's I, the counter. So I'll put an I right here. Voila. This should do the trick. So if I enter rubbish right here, 1 and 3, I still didn't open an input dialog. So let's open an input dialog. A is equal to input dialog with the prompt and the title with 1 line. Okay, so run. Let's enter rubbish here, and I want 3 constraints. So there they are. If I prolongate this, can't prolongate this. Wait, I think there's a way. If you hit F1, you've got options right here. Okay, and with options, you could control. Do you want to resize your window or not? So if you want that, let's define options.resize equal to on, and I'll pass options. And let me do the same thing here. So options.resize, copy it here, and I'll pass it here. Let me see if it works right off the first window. So there you go. We can resize our window. Previously, that was not possible. So if I turn this back to off, I cannot resize the window. So I'll keep it on, and happy resizing. Okay. So 1, 3, and there's an error saying default answer must be. So yeah, you have to pass your default text before. So default text in my case here is going to be nothing. I'll leave the user to figure it out because it's easy what I'm saying, right? Run, say the vector is 1, 2. Minimize, let's say 3. There's still an error. Also, this guy should be a cell. 1, 2, 1, 3. There you go, and there you can resize. Inequality constraints data. Of course, I'm not, worried about the graphical user interface because that's not the topic of this lesson. No, it's just to implement a nice mini software to do simplex. The first one is a less than, the second one is a less than as well, and the third one is a equal. Where are all those stored? They should be stored in A, but A is, it changes per iteration, so I'm going to keep track of those inequality or equality constraints. So the way I can do this is I'm going to open a struct right here. So struct is equal to a struct that contains my variables, which is currently set to empty, and it also contains their types. I'll talk about the variables later on. Now the types are which sense. Is it left, right, or equal? I'm going to store them in this struct, and I'm not going to call it struct, I'll call it struct1, because struct is already preserved. So struct1 at each iteration, so 1i dot type is simply a, and a1, right? Because it's already a cell. So run whatever here, I don't care, whatever here, I don't care, and here I'm going to put 2. Line 14, no, we do care. So 1, 2, 2, 2, less than or equal, and greater than or equal. Now let's see if they're stored here. This is struct dot type. Got less than and greater than. Okay, it's a 1 by 2 struct. Of course, the var I are currently empty, right? Okay, so this is my second window. I'm done with it. And we talked here about the sense of each inequality constraint. We saved them. And here I had my first window. Okay, good. Now let's go to the third window. What else do we need to form this problem? So, we read those, right? We also read, what else did we read? We read the senses right here. We still need those coefficients and those values, the bounds right here, right? To finalize the input, to formulate our linear program. So the third window will take a matrix. And we're going to call this matrix A, because the way I see it, or anyone should see this, is in the form A x less than a vector B, right? This is the vector, this is the matrix A. Okay? So we're going to read this matrix A. So again, title, we'll call it Inequality Coefficients, which doesn't make sense. This should be inequality constraint coefficients, right? So this is my title, and my prompt is only going to be, give me matrix A. Just give it to me. Okay, so this is my prompt, and default text, I'm going to tell the user that be careful, you have to enter a matrix. And not any matrix, a MATLAB matrix. MATLAB matrix. But the user is not going to see this comment, so give me a MATLAB matrix A. And what we mean by MATLAB matrix is that you have to enter it as follows. So let's say I want to, have a 2 by 2 matrix, which contains the values 1, 2, 3, 4, 1, 2 along the first row, and 3, 4 along the second row. So in MATLAB, you input it as follows. So 1, 2, semicolon to go to another row, 3, 4. And there you have it. So this is how we're going to input the matrix. Okay, now input dialog again, prompt. You know what? I might just copy paste all this as it is. Because really, taking a prompt, a title, one line, default text, and options which sets resize to on, right? Good. And I'll take the matrix A and evaluate it from the input dialog. Okay. Last but not least, fourth and last window is going to be the vector b. Again, title is inequality bounds. Could be upper or lower, depends on the sense of the inequality. The prompt is going to be, so right here, let me emphasize that it could be upper or lower. The prompt is going to be, give me vector b. And not any vector, a MATLAB vector. Well, the MATLAB vector is easily understood. You just enter white spaces between elements or commas, right? So 1, 2, 3 is the equivalent of 1, 2, 3. Good. So yeah, this is my vector b. Again, default text. I'll put this vector. The same dialog and the same evaluation. So, but instead of a, I'll call it b. Let's run to make sure everything is working properly. So let's say I've got the problem I had right here. So my C vector would be 1000 and 1200. So 1000 and 1200. I'm maximizing and I had 4 constraints. All my constraints had a less than sign, right? Constraint number 2, constraint number 3. Why are they going right here on the edge? I don't know. That's weird. And here, give me my matrix A. So my matrix A right here would be 5, 2, then 2, 3, then 1, 0, then 0, 1. So 5, 2, 1, 3, 1, 0, 0, 1. Good. Now my vector B would be 200, 60, 34, and 14. 200, 60, 34, and 14. Where's my solution? Well, of course there's no solution. I still didn't write it yet. So, but we can make sure that everything is going well. So let's print A. A contains my matrix A, B contains my vector B, C contains my coefficients of the cost function, and struct 1 will contain in the dot type all the inequality sense, if it's less than or greater than or equal. Now let's do the fun stuff. Now we're going to do those stuff because, as we said, the program is made to be for lazy people. So I'm lazy and I would like to just have a program that, you know, maybe I forget what a slack variable means, maybe I forget what a surplus variable means. I just want the program to do it for me. So right now I know what it means. Maybe tomorrow I forget. So this block of code is going to handle this for me. So right here I'm going to deal with slack variables, surplus variables, and we're also going to, you know, decide which variables are non-basic. Do we call them non-basic? Yeah, non-basic. Well, some people call them activity variables. Well, in French it's called activité, so it comes from there. Okay, so first things first. So for each constraint, I'm going to do something. So first, I'm going to extract the type, whether it's less than and greater than, right? And we're going to do some cases. So switch end, okay? Now, we have 3 cases. If it's a less than, if it's a greater than, or if it's an equal. Right here, we're going to store a bunch of variables. We're going to save them for later use. And yeah, so the slack variables, we will denote them as VE. So VE is a vector of slack variables, and it's going to you know, contain their values. So first we initialize it to be an empty vector. So that's VE. And yeah, so when we have a less than, we're sure it's a slack. So this is my slack. Okay. So we're going to add a slack. And how much we're going to add it is, so since all were less than, means, so let's start with the first one, it's less than, so we need a slack variable, x3. And how much are we going to initialize it? We're going to initialize it by 200, as the first iteration did. So here, they were 200, 60, 34, and 14. My slacks were 260, 34, and 14, and those are the values of my b vector. So at each iteration, I'm going to add a slack with value bi. Okay, I'm going to have a vector or a matrix, you know, keeping track of the coefficients of my slack variable, so I'm going to insert a 1 when needed if it's a slack. So the way I can do this is A1 is going to be, or I'll call it, so A1 is a vector for the slacks, as a matrix for the slacks, matrix for slacks. So A1 is going to append those coefficients. So at constraint I, and the current size of length VE, because the size or the length of VE is changing per iteration. What if the user entered a less than, then he entered a greater than, or she entered a less than, and switched all over, you know? So to keep track of this mixture, we're going to allow the length of VE to change. Because if, let's say we had 3 constraints, the first one is a less than, then at iteration 2, we need an artificial or a surplus. So there's going to be another matrix here, call it A2, with a length of V artificial vary, or V underscore. Let me insert underscores right here, it's better. So underscore, it's going to be set to 1, right? And here as well. And V array, like VE, is going to append the bound. Okay, we need to initialize V array then as artificial or surplus. We need a 2 then. And in this case, my slack will be 0. I don't have any slack. And at the same time, I have to update A1 to be -1 instead of 1. Okay, looks good. And when I have an equal, I'll just say I'll add an artificial. A2, I'll copy paste this. And in any case, I'm going to also keep track of my VB vector. So this is the vector of bounds. It's just going to be B, right? And this one was the matrix for surpluses. So at each iteration, I'll just append BI as such. My matrix A would be now augmented. A is no longer only my coefficients. It would also contain my slacks and my surpluses if they exist. So it's going to be A appending A1 slacks and A2 the artificials. Now I need, for printing on the console, I need the program to automatically generate my unknowns x1, x2, x3 down to x6. I know I can do this using one vector x, which is of size 1 by 6 or 6 by 1, but I need symbols. I need to see at each iteration which vectors or which variables are entering and which ones are leaving. Okay, it's better for educational purposes. So the way I can do this is keep track of my variables that are currently in the problem. Also, I'm going to divide my variables into 3 categories: the artificials or surplus, the slacks, and the basics or non-basic, the activity variables. And I'm going to iterate from 1 till how many. So the second size of A, the second dimension, would contain, in this case, 6. It would be the number of all the variables I have at the moment, which is 6 in this case. Let's check to make sure. So run, the cost is 1,000 and 1,200, maximizing, 4 constraints. Let's see what they were. 10, 5, or less than. Actually, all of them are less than. Shit. So let's do it again. 1,000 and 1,200. Minimize, maximize, 4. Now I'm not going to, type code for error handling. Like what if the user entered 3, not 2, and these kind of stuff. I'll leave those to you. The matrix A is 10, 5, 2, 3, 1, 0, and 0, 1. And the vector is, I'll just, put anything for the moment. 100, 60, 200, 60, 34. We have a problem. So VE. Now, do I still have A? Do I still have B? So I don't need to enter them again. I could just copy paste this code or evaluate. Can I just run selection or run evaluate current section? Okay, so I just ran only this section. Let's see, VE. So VE, the slacks are 200 down to 14. Correct. On A1, the slack coefficients are those, which you see right here. That's A1. A2 is null. I don't have any artificial. Okay. What else do I have? I have A, exactly. So A contains of the first two columns are the inequality coefficients, constraint coefficients, and right next to it you have the identity matrix. So altogether, this matrix is the first table right here in A. Okay? Now, what I meant to say here is that the second dimension, which is the number of columns of A, is the total number of variables, which is 6. So 6 times I have to now split. Which ones are my non-basic, which ones are my slacks, and which ones are my surplus? The way I can do this is simply as such. And I need to store them in a certain, vector. And that's why over here I had a struct with var I. So var I is going to be playing this role. Okay? So struct 1i dot var I is equal to, I would like to name them as such, x1, x2, x3, and so on. So x appended by, so at iteration I have xi in my hand. Now what I'm going to do with it is that I'm going to append it to var I, first of all, as such, and I'm going to do the following comparison. If the size is less than, in our case, 2, right? So based on that, we chose the non-basic variables, right? So if it's less than length of C, which is 2, right? Append the variables in the non-basic vector, which is var I underscore A. So struct 1i dot var I. We're saving them in a sentence because we're going to print them later on. So this is my activity right here, variables. It's going to be x1, x2, that's it. For this example that we showed right here. So this is for my activity variables. Else if I less than or equal to c plus length v underscore e, which is in this case length v underscore e. Let's see, it's 4 containing all the slacks. So this is 6. So right here I should be saving my slacks, right? I'll just copy paste all this because I just want to append them in a sentence, right? Else there I underscore artificial, I'll be appending the artificial ones later on, which we did not cover in this example. So I evaluated this right now. So var I contains x1 down to x10. And why is that? Oh, because A now contains this. So I have to, let me reset A to A1, 2, as it would be, right? So I don't want to run the program again because it will clear everything. I just want A to B as the user gave it to me, right? Run again. Okay, that's correct. Now v underscore a r I. So vary would be x1 down to x6, the name of my variables. Vary underscore a, the basic variables. Vary underscore e, the slack variables. And vary underscore ar, the artificial variables. Okay, now we divided the work. Now we divided everything. Now it's time to, okay, one thing we didn't do is initialize the non-basic variables to zeros. Okay, so I might as well do this, 0 times c. That works well, right? Because I want something like this. They're set to 0 and 0. Since c is of size 1 by 2, which is the size of which is also the number of, 2 is the number of my non-basic variables. So I'll just do this, which means that they're set to zeros. Okay? Now I need a vector of all my variables. So x1 down to x2, which is VA. I need my slack and my artificial, right? So if I execute this, I'll get 0, 0, and such. Those are my slacks. Those are my non-basic. We didn't initialize our artificial variables. Let's do that. I mean, here they're empty, right? And here they're denoted as x3 down to x4. But right here, we're only appending bi. So usually what people do, well, first, if I don't have, if is empty, if this is empty, means there's no artificial variables, then we're not going to initialize anything. Else, if it's a maximization problem, wait, was it maximum or minimum? So 1 for maximum. Okay, so if it's a maximization problem, initialize it to a very large number. So I'll just put minus 9999 v underscore AR times 1s. Else, I'll do the opposite. It's positive. This is a tradition. This is a classical way of initializing it. So if I execute it, now we get empty because we don't have any artificial variables. Now let's initialize CI, ZIs, or Js, whatever you want to call it. So my CJs, they are Cs appended by zeros. So 0 times how many VEs I have, appended by any artificial variables, if any. So if I execute this, my CJ would be as such. Right here. It's the same thing. Now, I'm going to need a CI to update per iteration. I'm going to need a table separator. I'm also going to need a vector to update my B's and a queue as well. Now, if I go ahead and execute this, Q contains the current values of the B's, right? So for each value of B, I'm going to create a row to start my simplex, okay? Now each row is going to have a separator just for printing purposes. I'm going to save the value of B, so the value QI, and I'm going to find the index where X is QI. For that index, I'm going to update my base variable. So struct2 is struct1, where I update my VB, which is going to be this. It's going to be the sentence I want to print, right? And you could, what I'm doing is just for printing purposes, so it's not that critical, right? Now the Z is nothing other than the C's multiplied by the B's and then added up. So it's the sum of the C's with the B's at the moment, right? And now I want to compute the ZJs, which is this column by this column and add it up, okay? So for each such, we're not letting Q, no, I want bigger one. So CJ, ZJ, I is the inner product between my CI's and the ith column of A. So if I run this, so struct1 is undefined, so I pronounce it so struct as such. Wait again, it's all good. So ZJ is all zeros. Is it all zeros? Yes. Let's check CJ minus ZJ. That's correct. Now Z, and that's correct. Okay. Now let's go ahead and print. So fprintf, let's go to a new line. And here, the first thing I'm going to print is LP in standard form. So what do we have? What has my program done so far in the sense of splitting the variables? So what variables do I have? I've got var I, right? Let me copy paste this 3 more times. I need one for activity, one for slack, and one for artificial. So activity, slack, artificial. This is an activity. And here I want to var I underscore a. I'll copy paste this instead of those. Slack and artificial. I underscore e. Here I need an AR, right? So at iteration 0, where is simplex at the moment? So I want to show the values of the activity, slack, and artificials. What do? First, let me display a message saying I'm initializing my variables. Initializing my variables. And they are var I, x1 down to x6 in the previous example. And as before, I need 3 more printings. One for activity or non-basic, one for slack, and one for artificial or surplus. Well, I'm not printing the same thing. No, I'm going to print the values. So num to string, value is v underscore a. Same here, value is v underscore e. And the same here, the value is v underscore ar. I would also like to print my cj, right? And it will be equal to cj. Let's give this a try. Okay, look what we have here. So x1 down to x6, and those are for this problem again, the one we saw step by step. Okay? I should be able to see, I want to see all this information printed at the MATLAB console. That's what I'm trying to do. So x1, x2 are the non-basic, that's correct. x3 down to x6 are the slack, and no surplus. Their values are 0, 0, 263, that's correct. And this is the value of my cj. Okay, I would also like to print zj. So zj, num to string zj. I want to print cj minus zj as we did here. So zj, c minus z, and then z, right? Zj, and then only z. Okay, so run. There you have it. Okay, this is the first iteration. Now we're going to start with the iterations on simplex. So I need a counter, iteration number. Set it to 1 because I already did iteration 0 right here. And I need an infinite while loop, so while true, and for the moment I'll just say while iteration number is less than or equal to 10. Because what if I do something that is not correct? I would like to, exit the while loop after 10 times of iterations, okay? Now at each iteration, I want to print the same stuff I had here. So enter, leave, pilot, the table at the simplex table at its corresponding iteration, and zj, cj minus zj, and z. So I'm going to start from bottom up. So I'll copy paste those 4 right here. Okay? Those values are going to be updated per iteration. That's what it means. Now I need the following. So there's one more thing I would like to print over here, which is what I have, right? So I'll insert some pipelines first. I want the simplex table. So display, and right here goes the simplex table. So display table, num to string. I want to print my CIs as here. So CIs right here, and tabulation again. And I want something to keep track of my variables. So if you recall, struct2 was keeping track of that, so I'll call a variable L, or vars at moment empty, and for I from 1 to number of constraints, if the length of my struct var is 2, do this, else do that, and here I'll just append with some space, okay? Else, I don't need any space. Going back here, I'll print my variables. Did I call it? Bars at moment, some tabulation. I need my Q matrix, string, some tabulation. I need my A matrix, and some tabulation. Let's see how this looks like. I'm going to run it without this while loop because I'm not done with it yet. So evaluate current section, and vars at moment is undefined. So yeah, because I'm evaluating this section. So let me remove this block right here, run it again. This is what I have. So zeros, x1, x2, x3, x4, exactly. So this is my C's right here, current variables, bounds. Go to iteration 0 because those are the values, and all this table right here with the C's, the Z's, the C minus Z, and Z. Actually, I don't need the C's. Let me put it right here on the top. Evaluate again. There you have it on the top. It's better on the top to keep things consistent. So I had it here on the top. That's why I'm doing that. Okay, so now let me update the loop. I would like to print the same information per loop. Okay, so I'm going to copy paste all this right here. Make me some more space. Looks good. On top of that, I want to know the current iteration. So I'll insert num to string, and it's iteration number that is telling me what is the number of iteration. Okay, and I would like some information right here, like display who's entering, enter. I get to see which variable is entering. I still didn't initialize this, so we'll see it later on. And I want who's leaving and the pivot. Leave and pivot. The same exact way I did here. Enter, leave, pivot. Okay, V, enter, V, leave, and V, or I'm just going to pick a pivot per iteration. I'm not going to save it. Okay, good. Now we're ready to start the simplex. So I'm first going to do a distinction between if I have a maximization problem. By the way, there's a lot of implementations of simplex. I'm just showing one possible way. So if it's a maximization problem, I'm going to first pick the max of the difference between Cj and Zj, so that we know where the pivot is. We need the maximum, right? This is only when the problem is maximum. And if there's many maximums, the same value, so let's say I had 1,200 and 1,200, I just want one of them. So if this is a vector, just give me one. Now I want to find which one. So at which index is it? So this one. And if there's multiple, pick one, right? Now the one that should enter, the variable that should enter, is in fact the one sitting at this index in the struct, right? Because they're already saved in the struct. So it's that one sitting at this index if it's a maximization problem. Otherwise, we're going to have the same logic but a min instead of max. So here I'm going to have a min. Let me call it something else. Maybe let's say G, and go to G. This is max and this is a min. And this guy right here is for entering variable. We still don't know who's leaving because we still don't know who the pivot is. We know which column it is, right? And we know which variable is going to enter, but we still don't know which one is going to leave. So now we're going to work on that. So we're going to pick this row or column which contains the pivot. It's B. And we're going to start a counter. We'll set this to 1E4. Now for I equal to 1 to length Q, if my BI is positive, divide, it's strictly positive, divide, because the negative ones I don't want. Divide this value by the corresponding, value in this column. That's what we're doing. If D greater than the division, then D is the division, keeping track of the maximum. And set K equal to I, to know the index. At this moment, I should know who the pivot is. Now, if I didn't succeed to get a pivot, so if my K, the one that's counting, is not 0, well, if it is 0, I mean, if we didn't succeed to get the pivot, means we don't have a solution, or the solution is infinity. Problem is not well posed. And get out of the loop. There's no use of repeating this step, simplex steps, because you're not going anywhere. There's no solution. Otherwise, save your pivot index in num2. Now let's say we want to know who's leaving. So vleave. Vleave is the one that contains the pivot. So let's first get its name. So it's stored in struct2 on num2 dot var underscore base. Let's get the index. The one that is leaving is in struct1. And the pivot, we're going to extract it using A, num2, the row, and num1, the column. Okay, looks good. Now we're going to update CI, and the A matrix, we're going to divide by the pivot. Remember this step? It was this right here. So the one, usually people do it from the very beginning. I didn't put it here because it was already 1, the pivot. Here we set it in the end, and here, there you have it. So usually you should always begin by dividing to normalize the row with respect to the pivot. So that's what we did right here. And now we're going to divide everything by the pivot as well. And now let's get the current size of the number of variables. Now iterate over that, except for the pivot, because we don't want to do anything with that column anymore. So except for where the pivot is sitting, right? Do the row operation. So row minus. So the good thing about normalizing with respect to the pivot is that it's 1. It's easy to, do the row operations, because all you have to do is subtract by 3 times R4. And here 5 times R4. So in our case it's A I num1 times Q2 num2. Q num2, right? This is for updating the Q's or the B's. Now update the row in the same way. So minus AI num1 times A num2. Okay? Now we need 3 more things. Zj, Cj minus Zj, and Z. How do we do that? Well, we said Z is the easiest one. It's just computing the cost, which is the Q's or the B's right here, multiplied by the C's, and then added up. So Z is the sum of my Ci's with the Q's, right? Next, let's update my Zj's, which are here or here. How do we do that? We said it's this column with this column with this. So for I from 1 till size, number of columns, Zji is the sum of Ci transpose pointwise multiplied by the row or the column. And the Cj minus Zj is easily obtained by subtracting. And now for printing, we need to update the variable at the moment. So I'm just going to copy paste this piece of code right here. Okay. And I'm going to flush it or reset it as such. Where are we? We're here. as such. Okay, so we're appending the variables at the moment, right? And that's basically it. So let's hope this works. Oh, we need a stopping criteria. Hold on a second. We need a stopping criteria. So I'm going to go down here and type stopping criterion. Now, the problem we showed was a maximization problem. So if it was a maximization problem, then we need all the differences to be negative. So I'll take the max. If the max of Cj minus Zj is negative, means all of them are negative, right? Actually, less than or equal to 0, because we allowed zeros. We're done. So break. If it's a minimization problem, then it's the same logic, except that you need the minimum to be greater than or equal to 0. So you need all of them to be positive. Now, look, we have a problem here. What if we have multiple maximas? Let's store this in a vector. So temp. So this is the max right here, and take only the first element, right? What if we have multiple identical elements? Same thing here. The temp is the min. Take one of them and argue upon that. Okay? And break. I'm going to keep this as iteration number less than 10, just in case I did something wrong. So run, there's an error. So what is the error? Input to num to string must be numeric. Of course, it should be numeric. What did I do? So iteration 1, the problem was here, v enter. Let's see how it looks like. Oh, okay. So there shouldn't be any num to string right here. Why did I do that? It should only be var I. Okay, there's one error here. So this block right here should be over here because we want to do the checking right before we start the loop. Okay, now we're ready to test our program. So let's run. First of all, the coefficients are 1000 and 1200. Next off, we have a maximization problem with 4 constraints, all of which have the same sense of inequality. Next, the matrix here is 10, 5, 2, 3, 1, 0, and 0, 1. And the vector B, 200, 6, 34, and 14. And there you have it. So let's check if we did the same iterations. And we'll compare. So at iteration 1, which is all here, what we computed is right here. So 10, 2, 1, 0, 10, 2, 1, 0, 130, 18, 34, 14. Okay. X3, 4, 5, 2, right? 1200. And looks good. 2 enters, 6 leaves with a pivot of 1. And here's my difference. Cj minus Zj is 1000 and minus 1200. This is the cost right here. So iteration 1 as well. Let's check iteration 2, 25, 800. That's correct. Cj minus Zj is correct. All looks good. And last but not least, iteration 3 gives me 6 enters and 3 leaves, pivot of 10. Cost is 27,000. And the optimal solutions are x1 equal to 15 and x2 equal to 10, as we saw right here. Now let me show you another way to make sure. MATLAB has its own optimization toolbox. I'm going to open a new script, call it test MATLAB opt as such. And we're going to make sure if indeed we get an x1 equal to 15, x2 equal to 10, and thus a cost of 27,000. So the way you do that in MATLAB is using the linprog toolbox. Okay, the linprog toolbox, we hit F1, solves a problem the following form. So F transpose X, it doesn't necessarily use simplex, It has a lot of options to use. One algorithm to use is simplex. So if I type simplex, it has simplex. Let's see what algorithms does it have. So as you can see right here, all those algorithms you can use, they're in this toolbox. One of which is simplex and dual simplex. There's other methods worth noting which are also really efficient and have their own properties, such as interior point methods and the active set method. We'll talk about those in further lectures. For this one, we're going to focus on simplex. Dual simplex is a variation of simplex with more properties. Now, we're going to run this algorithm using simplex. So, we're going to pass it three parameters, f, a, and b, where f, a, and b are f is the c vector, a is the a matrix, and b is the b vector, which we previously inserted in our method. So, to define them, f is minus 1000 minus 1200. So to define them, f is 1000, 1200, like here. It's same exactly as the c, so f is c. The a matrix is also the same, namely it's 10, 5, 2, 3, 1, 0, and 0, 1. B is 200, 60, 34, and 14. Be careful, it has to be a column vector. Okay, those are FAB. FAB is the traditional way, so if I run it as such, run, you get something really weird. Now let's bound our problem. That's why I was going to enter additional parameters. So you have A equality, B equality, and the bounds on X. So let's input those. We don't have any equality, so we'll leave them empty. We don't have any starting value. However, the lower bound, which should be inputted, I think, is all zeros, reflecting this, or namely this constraint. And we didn't specify simplex, so that's another issue. And let's put an upper bound of a high value, so 10,000 maybe. So 10,000 per, we've got two variables, not four. Okay, so run. It's still lowered. Well, we didn't input it to the function. So A equality, B equality, lower bound and upper bound. Run. We still didn't specify simplex. Okay, so this is what we're getting. Oh, so there's one stupid thing we didn't. This is a minimization problem, and what we had is a maximization problem. So we just insert negatives in the coefficients. Okay, right, so here I'm going to have minus 1000, minus 1200, run, and there you go, 15 and 10, and we didn't specify simplex, so I don't know which algorithm was executed. So let's see the default. The default algorithm is the interior point legacy. We're interested in simplex, so let's mention that. Options. So the options I'm going to input are the optimization options, right? So we're using linear programming, and we'd like to specify the algorithm, which is simplex, and I'd like to display some information at every iteration. So run that. There's an error. So right here we should have x0. Run, and there you go. So exactly 3 iterations. You see a negative here because we inserted the negative for the minimization problem. So we see that we get the same value at every iteration. Let me shrink this, put it here. At iteration 1, we get 16,800. Iteration 2, 25,800, and 27,000. The optimal values are 15 and 10. And that's it for simplex. That's all I have to say. We showed you one example. Let's see, I'm curious if I run another algorithm. Let's say the active set. So let me put here active set. We get the same value, but let's run the dual simplex as well. Dual simplex, 15 and 10. And here's some information. It shows you also the time, how much time it took. Okay, that's all I have to say for simplex. Just wanted to show you this figure of Dantzig. This is Dantzig, the guy who created simplex, and this is a figure right next to him. It shows you geometrically what's going on. So Dantzig chooses a starting vertex. We saw an example in 2D. This is easily generalized towards ND. But what Dantzig basically does is that we The interpretation of the simplex algorithm is that you first pick a starting vertex. It's when you set x1 and x2 to 0 and pick x3 down till x6 to be the bounds, right? This is equivalent to saying you're choosing a starting vertex. And then at each iteration, you're moving to another vertex. Simple as that. So if we were to see that, the vertex right here in the slack space, or when we introduced 4 other variables, was so right here 0, 0, 260, 34, 14. So in 6D, this is my starting vertex. After the first iteration, I am on x1 is still 0, x2 is 14, x3 is 130, x4 is 18, x5 is 34, and x6 is, where is x6? 0. Then at iteration 2, I am at 9, 14, 40, x4 is 0, x5 is 25, and x6 is 0. Last but not least, x1 is 15, x2 is 10, the optimal solution. x3 and x4 are both zeros. x5 is 19 and x6 is 4. Okay, so as you can see, we're jumping from a vertex to a vertex, as is depicted in this figure. Now, one thing worth noting is the time complexity of the simplex method. So you have to pay attention that here we're jumping from vertex to vertex and we're doing some operations. So it really depends on the nature of the problem. So there's a lot of arguments around, are you in your worst case? Is it the average case, which is a probabilistic average over all possible vertices of the feasible set we're working on, and you've got a best case. Okay? Now, the worst case is when you visit all the vertices of the problem, which in n dimensions is exponential. It's of order 2 power n. Now, this could be really slow. So when your n is small, there's no problem. But for a large number of constraints, this could be really, really slow. You can try to run simplex on a problem that has a lot of constraints, and you can see how slow it is. There's actually some papers for those interested in the time complexity of simplex. I found this paper by a professor in MIT, Daniel Spielman, another one in Boston University, and his name is Changhua Teng. I hope I pronounced it correctly. So this paper actually talks about the smooth analysis of algorithms, why the simplex algorithm usually takes polynomial time. So I think what they're talking about here is the average case. So it's polynomial time, okay? For those interested in this, they could take a look at this paper. There's another paper that I found really interesting. It's still an archive, I think, and it's called The Complexity of the Simplex Method. They have 2 results concerning the simplex complexity. So yeah, that's basically it. That's all I have to say in this lecture. We talked about a lot of stuff. We talked about what linear programs are, how to reformulate them in standard form, and we talked about 2 standard forms. We gave an example of the diet problem, in case you're on a diet or not, and we talked about one possible solver, which is called the simplex method, introduced by Dantzig. We showed an example, a step-by-step example. We implemented this on MATLAB. So now you have a graphical user interface to run your simplex method as such, or if not, you could just use the linear programming toolbox by MATLAB. And last but not least, we argued a bit about the time complexity of the simplex method. That's it for this one. If you found this lecture interesting, please support the channel and leave a like on the video. You can also subscribe to the channel. Thanks a lot. I'll see you in the next one.